All right. So today we're going to cover regression trees, not classification trees yet. You guys have seen some trees? Some of you? Some yes, some no. Okay. So even though this is lab day, this is actually a big day because this is the first time we're going to do a method that's really fundamentally nonlinear, right? We've kind of done nonlinear in a tricky way by putting nonlinear features into our feature set. But today is the first time we're going to do a model that's like intrinsically nonlinear, right? The prediction functions are not like W transpose X or W transpose psi of X. These are completely different. So just regression trees today. We'll do classification trees at the beginning of next week is the plan. All right. So we've walked through this a little bit before. In a regression tree, you start with an input X, and you generally look at one feature at a time. Like, so maybe our input is this vector representing a picture, and these aren't realistic decision questions, but intuitively, like the first node is the top part blue? If yes, go right. Is the bottom part blue? If no, go left. So this is, you work your way down the tree by answering a question at every node. Each of these circles is a node of the tree. And if it's true, you go right. If it's false, you go left. And when you get to the bottom, you have these things called leaf nodes or terminal nodes. And in each terminal node or leaf node, there's a single prediction. So any input that ends up in the same terminal node or leaf node gets the same prediction, no matter what. If it's regression, it's going to be the same number. If it's classification, it's going to be the same class. All right. OK. So already, this is very different from regression, because in any kind of linear classification, you only get this, well, you never have this kind of constant predictions in certain regions. It's always changing with some linear functions. So these predictions are piecewise constant, because in each node you're predicting the same thing, a constant thing. And when you jump to a neighboring node or region, it's going to jump to another value. So it's discontinuous and constant on parts. All right. So the trees we're considering today are binary trees, which mean the splits are always into two parts. And moreover, the splits are based on a single feature at a time. So we're not going to have any complicated questions. It's always going to be, is a particular feature value, at least for continuous things, continuous feature value less than or greater than some threshold? That's what we'll start with. All right. And as we mentioned, I think in the second lecture, this type of decision tree partitions the space into regions. Every leaf node corresponds to a different region of the space. Is it clear why the individual regions are all rectangular with the axis-aligned sides? Yeah, clear. Great. All right. So once we have our regions, so the splits, the decisions at each node give us our regions. And then with each region, we need to assign a value. So in regression, we'll assign a numeric value to each of these regions. And in classification, we'll assign a class. Fine. So here's a picture of regression, where in each of the regions, we have a different value that we're predicting. Notice that it's constant on the regions. OK. So let's formalize it a bit. A decision tree partitions a input space into regions, which we'll call R1 through Rm. So M regions that we are dealing with. And so to remind you, a partition is a disjoint union, which means each of these regions they have no intersection, but when you union them all together, it's the whole input space. All right. And one way to model the prediction function, we want to write down this prediction function, f of x. And one way to write it is as a summation over all the regions. And if we take a point x, we write these indicator functions. Indicator for x being in region M, right? And this piece is a 1 if it's in the region and a 0 otherwise. So of course, a point can only be in one region because the regions are disjoint. So when we sum over these functions, it will only be 1 for a single m, and the rest will be 0. And then the value of f of x will be just c of m, c sub m, where M is corresponding to the region that X was in. Are clear? How would you describe a particular region RM? How could you write that down? What's its shape? Yeah, it's always rectangular, or in higher dimensions, parallelepiped with the sides aligned to the coordinates. So you could write any of these regions as something like x1 is between 3 and 7, x2 is between -5 and 5. It's always every coordinate is within a particular interval. That's how you would describe one of these regions, RM. Okay. Very good. So suppose we're given the regions, how do we choose the C's to predict? Right? Well, we need a loss function to know how we want to do the prediction. Let's do square loss, because we're in the regression setting. It's the most standard. So I claim that if I tell you the region, the partition of the space into regions, it's quite clear what C's to choose to minimize the square error overall. So what you would do is, and I hope this is clear once you make the connection to some homework problems that you guys have done. What you do is you look at all the training points that are in a particular region, say RM, and you take the average of the Y values for all the points that land in that region, and that will minimize the square error for points in that region. Oh, is that clear? Is that familiar? That the average of some points minimizes the average of the Y's would minimize the square error for predicting those Y's? It's the exact same calculation you would do for when you looked to find the minimum risk prediction with squared error. That was on the first assignment. And you found it was the conditional mean. All right, well, a mean is an average. So it's the same calculation. Okay. Is that clear, or should I write that down? All right. You can post on Piazza if you're unclear. All right. So if someone gave us the partition, we know how to get the CMs. It's the average of some points. And in our model for building prediction functions, we usually have this trade-off between complexity and fitting, right? So the issue with trees is that if we make a whole lot of regions, then we might be overfitting. You could imagine you could have a region around every single point. If you didn't have any duplicate points, you could put every single input training point in its own cell, in its own partition, right? And then you could, of course, get all those points exactly right. You'd have zero training error, but that would likely overfit. So how are we going to constrain the complexity of trees to not overfit in that way? So one way is to find a measure of the complexity of a tree and restrict it, or maybe penalize the complexity of the tree. So we'll measure the complexity of the tree by how many leaf nodes it has. It's pretty reasonable. And so we'll write that as, call this the norm of T. If T is a tree, we could call this the size of T, say. It's the number of terminal nodes. All right. So one way is to say for a minimum complexity, so I want to have a tree with at most 20 terminal nodes. Then, given that constraint, I want to find the tree that has the minimum error on the training data in terms of minimizing loss. So that's a great approach, I think. It's just that computationally, we can't solve that problem, it turns out. So what exactly do I mean? We can't find the exact best tree of a certain size computationally. This is algorithmically, people have not figured out how to do it. People have proven, in fact, that you can't, well, almost proven that you can't do this efficiently. So what we're going to do is come up with an algorithm that is motivated by this idea of finding the best we can with a tree of a certain size, but we're not going to be able to actually minimize we're not going to be able to find the best tree of a certain size. All right. So we proceed with what's called a greedy algorithm, which is basically we're going to build this tree out one new node at a time, one decision at a time. And we're not going to do any looking ahead. That's what a greedy algorithm is. All right. So let's suppose our input space is d-dimensional. OK. So every time we split, we're choosing a coordinate or a feature. So maybe, I don't know, x3 or something. So we pick a particular coordinate, x3, and we're going to find a threshold, or we call it a split point s. And anything that's greater than s, we're going to send to the left, and everything that's smaller than s, we're going to send to the right. All right? So we need to find a variable to split on. I'm using the same several words for the same thing: variable, feature, coordinate. I'm talking about the entries in this d-dimensional input vector. All right. So for every split, we need to find the variable and the split point s. So let's do a little bit of notation here. Let's write R1 for a given j and s. J would be the variable and s would be the split point. Let's let R1 be everything to the left of the split and R2 be everything to the right. So that's going to refer to the partition given by the particular splitting variable and split point. All right. So given that split, that partition, well, we know how to find the optimal prediction on each of those partitions, right? It's the average of the y values that end up in each of these partitions. So I've written that down here. So C1 hat, C2 hat, that's going to be our prediction for C1 will be the prediction for things landing in R1. C2 would be the prediction for things landing in R2. For any given, I've written it all as a function of j and s so that we can kind of reuse these as functions. Any questions on notation? OK. All right. So this is the objective function that we need to minimize. Let's stare at this for a while. I want to make sure we understand it. We're looking at the total error that we're going to make when we predict for a given choice of splitting variable, split point, and actual prediction value C1 hat and C2 hat. So we're summing over all the points that are in both regions. So on the left, we're summing over the square errors on the points in region 1, and on the right, the square errors on the points in region 2. And you see that on the first sum, we're predicting C1 hat. And in the second sum, we're predicting C2 hat, because those are the two different regions. And then summing them together, we get the total error for the prediction across the union of these two regions. All right? OK. Any questions? All right. I will draw a picture. OK. So suppose we've already chosen the splitting variable. All right? So in that case, the problem is one-dimensional. Once we've chosen the splitting variable, suppose we chose the first coordinate, x1. So then I can draw x1 like this. All right? And now we want to look at the y values for all of our points in terms of x1. So suppose we have some points that look like this. I'm drawing y as a function of just x1. So is it clear? So maybe our original input vectors are 100-dimensional, but we've chosen a splitting variable, the first one, x1. And so I only plot the first coordinate of each of these points. And then on the y-axis, I plotted the thing we're trying to predict. OK. So we need to find a splitting point and C1 hat and C2 hat. So where should my splitting point be? OK, good. Right. And where should my prediction value be? Yeah, OK. So that's C1. This is R1. This is R2. This is C1 hat. C2 hat. Okay. All right. Cool. So we did that by eye. Question for you guys. How might you implement this? Is there a way to implement this efficiently? How do we find the split point? Let me phrase it differently. Do we have to check all possible points of x1 as the possible split point? Why not? No, why not?
Just because it doesn't change between the points.
Yes, because it doesn't change between the points. If we make the split point here, 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 nothing changes in the predictions or the loss. Right, so the split points, the only possible split points that one needs to check are when we split right at a data point. All right, so if there are n data points, we need to check n possible split points. But maybe that's not too bad. Once we have when we choose a split point, how do we find the square loss? That's pretty easy. We have a split. The prediction, we need the prediction value, so that's just all the average of all the points to the left, average of all the points to the right. Now you can imagine, like, from like a computer science perspective, there might be efficient ways to implement this. Like maybe you want to sort these and go from left to right, and maybe it's easy to compute the averages as you move from points. Anyway, so if you're going to implement a tree, you might think a bit about, or Google about efficient ways to implement this. But the key idea is that one only has to check the data points for possible splits. Okay. Great. Clear? All right. So this whole procedure tells us how to find one split. So we did it for x1, and then what you would do is you do it for x2, and you do it for x3, and you do it for all the way up to x100, and you try them all, and you see what gave the minimal square error, and that's the one you would choose. Right? All right, so that's solving this minimization problem. So we do that once, and we get the first split, and then what? Well, now we've gotten all our data, and we split it in half, and part of it now is in R1, and part of it is now in R2. And what happens next is you repeat the same process recursively. So you say, okay, let me take R1, all these points, and I'm going to do the exact same thing. I'm going to take these just this subset of points that landed in R1 and find the split for these and proceed recursively. And then same for R2. And then the only question is, when do you stop? Right? So there's a couple approaches. One would be you stop at a certain point to keep your trees from getting too complex. Like if you go too deep, then you'll have a very complex tree, and you'll be overfitting. That's a viable approach, and you could find ways to do that. We're going to do another approach, which is you build a really deep tree that's way too big and overfits, but then you trim it back and you throw out some splits. And this often is found to work better. It takes longer because it's a two-step process, but this method is called CART for classification and regression tree, and it works pretty well. Okay. So this is the recursive procedure I acted out for you. All right. All right. So the approach we're going to use is build a really big tree and then prune it back. So for example, a stopping criterion might be build the tree down until every region has fewer than 5 points. Right? So keep splitting until we have something of fewer than 5 points. All right. So this is terminology. The internal nodes are the splitting nodes. Terminal nodes or leaf nodes are that correspond to the classification or prediction nodes we've discussed. All right. Now subtree. What's a subtree? So if T0 is our full tree, growing all the way out until every node has, like, at most 5 points, T would be a subtree of that. So that just means we collapse regions and put them together. So if this is a full tree, you can see it gets very small, these splits at the bottom. So the subtree would be, for instance, if we took all of these regions and collapsed them and just only had one decision going left, right? So just collapsing decisions and saying, no, I no longer want to split this last time. I'm going to put anything in either of these regions together, and I'm going to make the same prediction for all those things. That's a subtree. So literally, it's like a subset of these splitting internal nodes. Here's a subtree. All right. So suppose we want to prune a big tree T0. Let's bring back our old concept of empirical risk, right? So we have empirical risk is the average loss on your training data. Good. And we can assess a tree in terms of empirical risk, which, yes, please.
Sorry, subtree should end up in leaves.
Can you say it again?
Subtree should end up in leaves.
A subtree takes these internal splitting nodes. I mean, every tree always ends up in leaves.
No, okay, I mean the internal ones. If it ends up with the internal ones, it's still a subtree. For example, the one node, the second node on the left.
Yes.
With two childs.
Okay, if we keep this splitting node,
Yeah.
then we'll still have these two leaves to the left and to the right.
Right. But
Yes.
you don't have the four leaves on them.
That's right.
And it's okay, it's a subtree.
That's a subtree. That is a subtree, right? It's when we leave off the bottom parts. The subtree is always leaving off things from the bottom. So
We exclude the roots as well.
can you say again? You keep the roots.
We can't.
Yeah, so a subtree will always have the root, and sometimes it'll keep going further down. The idea is that the top part of the tree is the most important stuff. And then as you get further down, it's doing fine detail. So you want to throw out this fine detail because this lower stuff may be overfitting. Yeah.
So the subtree should still get covered entirely.
So this question is, does the subtree still cover the entire input space? Yes, at any level, we're always covering the entire input space because any single point always either goes left or right. So it's always somewhere, yeah.
It's just a random question. Why this graph is so unbalanced?
Why is this tree so imbalanced?
No, I mean, there's so much space on
Why did they draw it this way? Huh? I was wondering the same thing. I don't know. I think it's because they didn't draw this specially for the book. They probably used some tree drawing software that wasn't very good. I don't know. Or maybe it's great and there's some really excellent reason why they do it this way, but I'm not familiar with that reason. So that is a pretty random question. Okay. Any more questions? All right. Okay. So r hat of t is the empirical risk of a tree t. Let's say we're doing square error. Fine. Now let t be a subtree of t naught. So when we take a subtree, is the empirical risk going to go up or down? The empirical risk will increase because we're throwing out the finer splits at the bottom. The more splits you have, you can only get better predictions. So if we throw these out, the empirical risk will get a little worse. So r hat t is a little bit worse than r hat t naught if t is a subtree of t naught. All right. So size of t is our measure of complexity. So we have our complexity measure, we have our empirical risk. So we feel like we can do some kind of regularization, right? So that's this cost complexity criterion. We have r hat of t plus alpha, our regularization parameter, times the size of t. So this is, we've called this form Tikhonov regularization, or penalized empirical risk minimization. So there's a problem, because what have we done before with things like this? What's our first step to try to minimize this? Gradient, right? Gradient descent. So usually there's a W, a vector of parameters that we differentiate with respect to. Here, There's this T, it's a tree. We can't differentiate with respect to a tree. It's not, the space of predictors is not something that's continuous. So that kind of approach isn't going to work. All right. So the approach is basically to build a big tree and prune it back one node at a time. And every time we take off a node, it gets a little bit smaller, becomes a subtree. We see what, so two things happen when we remove a leaf node, when we take away one split of a tree. The complexity goes, when we remove a split from a tree, the complexity increases or decreases? Right, and the empirical risk increases, exactly. All right, so we can keep doing that until we've removed every single node up to the root, right? And that gives us kind of a hierarchy of trees. All right, so how does this work? Our first step is we're finding a subtree, T1, that minimizes the empirical risk of T1 minus empirical risk of T0. What's that mean? So we want to find the subtree that it's smaller than T0, but it has the best possible empirical risk and still be smaller than T0. So basically this means you remove a single node, a single split, and the split you remove does the least damage to your empirical risk. So that would be T1. And then we go again and we find T2, and so on, all the way until we just have a single node. And this is a hierarchy of trees. And then you can look, for instance, at the performance on your validation set of each of these trees and choose the one that has the best performance. That would be an approach. Yeah?
So when you build up, you use greedy algorithm to do the split.
We use a greedy algorithm to build up the tree.
The same order, like back from.
So the question is, does the order that we put the nodes in, is it the same as the order in which they prune out? No. First of all, there's no order to the way we put them in, right? So we do a split. I can choose to split the right side or the left side next. Yeah, so there's no order to the splits. Yeah. Okay. All right, so we come up with this set of trees, and they're nested, and that one tree is always, since we remove one node at a time, each tree that we end up with is a subtree of the one we just came from. So T sub n, this is the original, no, T sub 0 is the original tree. T sub 1 is, we've removed one node, T sub 2 is two nodes, and we get n of them if there's n nodes. And there's this amazing thing. So Leo Breiman, who is a statistician who is one of the inventors of trees, he also invented random forest, which we'll come to later. He proved this pretty amazing thing, which was that this objective I wrote here, so finding a tree that minimizes this objective for a particular alpha will always give you a tree that's in this set. So that's what I wrote here in math. So argmin over all trees, where T0 is the full tree, all subtrees of T0, of this alpha penalized empirical risk. No matter what alpha you set, you're always going to end up with a tree that's in this kind of pruned hierarchy, this hierarchy of pruned trees. So this justifies the, if you believe in this approach of, let's penalize with how many nodes you have. Let's just do alpha times the number of nodes. And we can, try out different alphas. Well, that's equivalent to doing this greedy, this greedy pruning of nodes and choosing the one that works. So choosing among these trees is the same, that works best, is the same as choosing alpha that gives the best performance on validation. Any questions on that? Yeah.
So does the domain of the tree here is obtained from the way
Oh, I see. So this theorem is about the way we pruned the tree. So you start with the tree, you could have built it however you wanted to, and then this method of pruning where you find you prune it a little bit at a time, doing as little damage to the empirical risk as possible. That gives you a hierarchy of trees. Yeah, so this is specifically about that method. So here's just a little plot, kind of a regularization type curve we've seen before. On the x-axis, we have two labels, actually. We have alpha, that penalty regularization term, and the tree size that we end up with for a particular alpha. And on the y-axis, roughly speaking, we have the misclassification rate. So in this case, as the tree gets bigger, the misclassification rate gets smaller. So I'm a little puzzled by this. For me, this is an interesting curve, and I'm a little surprised by it. Does anyone know why I'm a little bit surprised by this curve? So this is supposed to plot test error. Yeah, so I would expect that it would eventually overfit and go up. So that's interesting. Perhaps it's some characteristic of the data set, or I'm not sure. I'm probably going to look into it and see what's going on there. Kind of interesting. This was from the Hasty Tibshani Friedman book.
What are the numbers on the top?
Yeah, so these are alphas. So an alpha is how much we're penalizing, the size of the tree. So big penalty, 176 for alpha, corresponds to a very small tree. And small alpha is the full tree. Yes?
How do they map back to alpha?
How do they?
So you know the number of nodes, you know the tree size.
Okay, so good question. So the question is, so you pick alpha, and then you can go through this set of trees, and for each one of these trees, you look at the cost complexity criterion. So we evaluate, you can pick each of these out. Pick an alpha. Then you run each of those trees through this expression and evaluate its C alpha t, and that gives you a number. You choose the tree that has the minimum, and that's the tree that's optimal for that alpha on the training set, on the training data. No. Okay. Cool. All right, so we're going to skip classification trees. Any questions on regression on these trees? Yeah.
At each level, given that we're going to pick a splitting variable and a splitting point that minimizes the square loss rate, is it possible that at a future level, at some level once you reach, that we pick a splitting variable that has already been?
Yes, the question is, can splitting variables repeat? Absolutely, yes. Uh-huh. Yes.
Another thought is, so it's always going with the gradient algorithm. So every time it's taking the optimal at that step. So it's also possible that you can somehow slow down first, and then it could actually give you a smaller loss in the end. But the regression tree algorithm here is not considering that.
That's true. So the question was, if we're doing a greedy approach, which we are, the choice of the split in the first step, the one that looks best from the first step, may lead to a tree that's worse overall than if we had chosen another split, which is not as good in the first step, but for whatever reason, the overall tree is better. Yeah, that's absolutely true. And yeah, that's kind of the point, that we don't know how to find the optimal, so we do this greedy approach instead. Mm-hmm. Yeah.
So once the tree is pruned, the values at each vertex or the terminal node is going to be recomputed, or you use the existing values and make an average?
Oh, so this is a computational question. Is there any kind of a shortcut for computing the new predictions in each terminal node based on a split? It's a good question. I don't know if there may be a way to do that more optimally. I'm not sure. I mean, the truth is that I don't know if there is a better way, because you have when you look to split a particular set of points. This is the first time you've looked at just a set of points. So you have to still look at every point to figure out where to split it. And so as you do that search, you're going to have the average values anyway. So just to figure out how to split the data, you're already going to be computing the values you want to predict on those two splits anyway. Yeah? No? Okay. Yes?
Like semantics. So when we talk about hierarchy, is there a direction that we're talking about, like complexity or error rate, where a bigger tree is further on the hierarchy and a small tree is lower on the hierarchy? Or
No, not really. So, no. I mean, I'd call this a nested sequence of trees, but I don't know of a higher or lower. I mean, I would say higher or lower complexity, but yeah. More questions? Yes.
Very expensive. Why?
Oh, great question. So you think this might be more expensive than the other methods we've used?
Yeah, for regression, I think. For
Mhm.
classification, I can understand. For
Okay, it's a good question. Do you guys have any ideas on why you might want to use trees?
It's interpretable.
Okay, so nonlinear. So this is the first method we've come up with that discovers nonlinearities for us. That's nice. It's potentially interpretable. Interpretation. You can look at a tree and say, you can explain it to somebody, right? We have this, if the years they've played is less than 4.5, we're going to predict 5.11. And if hits is less than 117.5, and you can look at a small tree and understand it. Now the tree has to actually be small to do that in any practical way. So a lot of people give interpretability as an argument for trees, but on the other hand, on a lot of data sets when you actually try a tree, the tree that's best is big and not really that interpretable. So that's questionable, but at least a small tree is very interpretable. Okay. And then maybe there's one or two other reasons we'll come to in a minute. Any more questions? Yes?
So the aim of tuning is choose the best tree, to choose the tree that gives the best error on the test data. Right?
Yes.
So why can't we do the same thing when building the tree? Like when doing empty split, you can calculate the error on the test set and then instead of doing a two-way process.
Well, okay, so the question is, can we decide our splits using the test data?
Yeah.
Well, if you think about it, that's basically training using your test data.
Not those splits, but the best split.
The best split. So it's a compromise. So you're saying, I don't understand. So for every variable, what do you mean by the best split? The best splitting variable, or the best split point, or what do you have in mind?
So first we do a split according to your training data.
Okay.
And then you store the error on the test data in some format.
Okay.
And by the time you build the entire tree, then you just you have an array of the errors in the test data, so you can just pick till when you can.
Oh, you mean, okay, I think I understand. So you're saying build your tree until the test error starts decreasing?
Yeah, that's one way of putting it.
Okay, that's an interesting stopping condition. That might be reasonable. Another thing is you can prune your tree based on the test data, perhaps. Yeah, it's always a tricky trade-off between about how much you want to use your test data to select the model. Or I've been saying test data, we really mean some kind of validation set, right? So the more you use it, the more at risk you are of overfitting your validation set. So it's a bit of a trade-off. You know. Yes.
So for the split variable, like how do we decide like which one you're going to use?
Which one you're going to use?
Yeah, which one you're going to repeat using especially? Like,
No, I mean, I don't decide, am I going to repeat it? In every point, I look for the best one. If it happens to be one I've already used before, that doesn't matter.
But so this algorithm would automatically so not only like the splitting point, but also the splitting variable it would search.
Yes. So what I was working through here was finding the split point for a particular split variable. So we find the best split point and predictions, and then we try the next variable. This was x1, then we try x2, and all the way to x100. And so we've tried all 100 split variables, and then we find the one that gave the best loss. That's why it's expensive, right? Okay. All right. So one reason people like trees, one other reason people like trees, is that you have a fairly reasonable way to handle missing values. Okay? So far we've never discussed what to do when you're missing a value, missing a particular feature value. Okay? So trees have one approach, which was kind of built into the definition of when people describe trees. Okay. So what do you do with missing features in general? One thing you can do is just say, all right, this input example is not usable. It's missing a feature, so throw it out. All right. Another thing you can do, which arguably is maybe a good thing to do, is to impute the value. Impute the value means guess what it is and just put a value in there. So there's lots of ways you can do it. The simplest way would be to replace the missing value with the average of all the other values for that feature from the other points that have it. Trees have another approach. You can do what's called make a surrogate split. So basically a surrogate split is for every splitting variable. So for every split, suppose we've chosen x1 as our split. Now we make a surrogate split, which means find another variable to use in that same place, at the same place in the tree, that we use as a backup in case x1's missing. So what does that mean? We want to, so suppose we've searched and found our best split at a particular node of the tree. And after we do that, we say, OK, now we need to make some backup plans for what to do with x1 is missing. So we search again through all the variables, and then we'll start with like x2, say. And we'll see how can we use x2 to make a split in the points that's as similar to the split that we got from x1 as possible. Is that clear? So basically, we have a split of x1. So a certain set of points are on my right, and a certain set of points are on the left. And now we come to x2, and we say, all right, how good an approximation to that same split can we get with x2? Or can we get with x3? And you see what kind of approximation you can get to that split with each of your variables. You sort them by how good those approximate splits are. And that's the order of things you use when you have missing features. That's a sketch of the idea, yeah.
Do you try to replicate the loss? Or
Nope, you try to replicate the split of the points. Yeah, try to replicate the splits, yeah.
So it's going to check all the features
Yeah.
to see which one is the best.
Yeah, you check all the features to see which one can give the best approximation of the same split. Yeah. So then it's almost more like a classification problem, right? We need to find a way to send all of a particular set of points that went to the right previously to the right with this other variable that we're splitting on. Yeah. Okay. Okay. So a lot of in practice, you probably won't build your own tree software very often, but most tree software you use has built into it nice and smooth handling of missing data. So down the road, we're going to build ensembles of trees with boosting or random forest. And since they use trees as their kind of fundamental unit, when you combine trees, as long as you're using trees that can handle missing values, these ensemble methods will also be able to handle missing values in the same way, which is nice. All right. Okay.
So does the surrogate happen automatically or
No, I mean the surrogate splitting, you have to do work to find the best surrogate splits. So some tree algorithms will do it and some won't. Yeah. I'm going to skip this. Yes? I apologize. I couldn't hear you. Can you repeat that? If we know the range of f of x, then we could be using tree algorithms. Why? We decide that we have the y values. We always go through the entire data every time we make a split. So yes, we certainly need to know not just the range, but the averages on each part of the split. Yeah, we're touching all those y values all the time. Certainly, yeah. All right. So here's another important difference, kind of a key difference between trees and all the other things we've done so far. It's what types of prediction functions can they do easily? What do I mean by easily? By easily, I mean with low complexity. So if we're measuring complexity of trees by how many leaf nodes there are, then let's look at this picture. So on the top two pictures, we have two regions. It could still be a regression problem. So green could be 1 and yellow could be -1, right? So with the linear model, it's easy to have you can imagine a prediction function that, well, say it's SVM, right? So we're thresholding our prediction function. So our prediction function could easily match this line and perfectly separate these two regions. But to get this diagonal line with trees is very difficult. It has to have lots of splits to even approximate this diagonal separation between the classes. Whereas with these box-shaped regions, linear has a very difficult time separating the regions. It has errors, whereas with trees, it can separate them exactly. So yes? Right, so it's indeed possible to have regions that are hard for both trees and linear. Yeah. So. Well, I mean, that's another type of nonlinearity, and you would just have to, you can approximate that with lots of splits with the trees. And with linear, you can only get nonlinearities if you build in more nonlinear features into your input space. So. All right, so wrap up on, so we talked about interpretability as a reason people like trees. Here's another reason. Trees can be a way to discover the nonlinear features that you want to use inside your linear models. That's interesting. So suppose you take some data and you build your tree, and it's slow, it takes a long time. But at the end, you get this prediction function where it's divided our space into these regions. So what you can do is take these regions as features in your linear model, right? So each of these regions can be used as a binary feature. Is this x in this region Rm, which is described by the sequence of inequalities on the coordinates from the tree? That would be a feature. And you can just take all these nonlinear features, or take the ones that you think are most useful, and throw them into lasso regression or something. So this is a way to automatically build some nonlinear features, which may actually be very useful for your problem, but then put them into a linear classifier. So why might we want to do this? How's time? We're almost over. Why might you want to do this? Maybe training on all your data is too expensive for trees, because trees are slow. OK, so take a subset of your data, perhaps, and build your model, and get some useful nonlinear features. and then plug those into Lasso and train on all your data. This would be a possible use case. No? Okay. All right, I think that's all I'll say about trees for today, and time's over anyway. So if you're sticking around for office hours, I'll see you then. Otherwise, I'll see you guys on Wednesday.